Hello, welcome to the new chapter. So it's going to be about Fourier series. So you watched last week the video of Three Blue, One Brown on that topic, and don't hesitate to watch that again because it's really some fantastic explanation of what's going on there. Okay, so if you remember in the video, we were approximating any curve that is drawn in the plane by something that were a sum, an infinite sum of exponential functions. Okay, but maybe we can begin first by looking at just real functions. So functions of x that give you a real value y. The idea is that how well can we approximate or get an exact value of this function with something like Fourier series, and we're just going to call that trigonometric series because, well, when you don't need the complex exponentials because you are just looking at real functions, we're just going to need the cosines and sines. Okay, so let's begin by this definition. A trigonometric series is just going to be a series that is defined by, we will have some constant coefficient and then an infinite sum of coefficient times some cosine and coefficient times some sine. Okay, and the values, the real values an and bn, so these infinite sequences are called the coefficients of the trigonometric series. And so if ever this infinite series is converging, let's say, to some function f of x, well, the first thing we can say is that the first result we're going to get is that if this f of x exists, it's going to be a 2pi periodic period, all right? Because I'm just summing 2pi periodic functions. Okay, now let's see the problem from the other side. Let's assume that you've got a 2pi periodic function called f, and that you can find a trigonometric series that is converging to this function f at every point of one of its period. Okay, so that indeed you would be able to write that f of x is equal to this infinite sum. All right. The question is now, how can we find the corresponding coefficients an and a0, an, and bn? Okay, so let's work on that. So let's begin by rewriting the formula we have. So let's assume that we know f of x can be written as, so we would have, we said some a0 over 2 plus some infinite sum from 1 to infinity of, we would have some an coefficients times some corresponding cosines, so nx plus some bn coefficients times some corresponding sines times nx, of nx. Okay, so all these terms go in the infinite sum. So now let's see what we can get. Let's do some integration of these each of those terms. Okay, so let me integrate that between negative pi and pi. Okay, as we said, if this is a converging series, the corresponding function should be 2pi periodic. Okay, so let's integrate on a period that whole stuff, right? Dx. So what do we have? So let's split that in two. We're going to have from negative pi to pi of a0 over 2 dx plus the integral, we should be careful about this. Okay, so let's not do it directly. So plus the integral of the infinite sum from 1 to infinity of, from negative pi to pi. Okay, let me rewrite that. So from negative pi to pi, infinite sum of 1 to infinity of an cos nx dx. Let's take them separately. Negative pi sum of bn sinus of nx dx. All right, 1 to infinity. First of all, we would like to be able to exchange the, as usual, the this series and the summation signs. So you know what we should do in that case. We should use Lebesgue dominated convergence theorem. Okay, so you know the one concerning the integral of a limit and the limit of the integral. So what would we need? We would need to find some function that is dominating our series, and well, in our case, maybe we could say that we will use let's assume that f is in L1 also, okay? In L1 of is integrable, and we only need integration on negative pi pi, okay? If f is in L1 of negative pi pi, because we're only integrating on that interval, that's what we're interested in, then we have that this sum, let's put that together, plus bn times the sinus of nx. All right, so that is going to be bounded from above by absolute value of f, okay, because they are almost equal to each other. All right, and so let's say that it's going to be, and if f is in L1, it's integrable, and then I can use Lebesgue's dominated convergence theorem. Okay, whatever. So let's say that we can perform this exchange of integration. So I still have this one, plus the infinite sum of an cosine nx dx from negative pi to pi, 1 infinity, plus same stuff for the sinus part. So, sinus. Okay, sum of bn negative pi pi sinus of nx dx. All right, let's have a look at these integrals. So you know you can integrate that. That's going to be 1 over n on the first case, 1 over n sinus nx between negative pi and pi. And so of course that's is going to be 0 because the sinus in negative pi and then pi is equal to 0. That's on one hand, and on the other hand, I have, so that will be 1 over n minus 1 over n cosine nx, okay, from negative pi to pi. And the thing is that the value in pi is going to be 1 over n, so negative 1 to the n, okay, that's going, well, minus 1 over n, negative 1 to the n, minus 1 over n, minus 1 over n, so that makes a plus negative 1 to the n, okay, because minus n pi. And anyway, you could even just play with the fact that the cosine is an even function, so to directly say that this would also be equal to 0. Okay, so what do we get in the end? The only non-zero term is going to be this one. Yes, so that one is negative pi pi a0 over 2 dx. And so that's 2 pi times a0 over 2. So that's a0 over 2 times 2 pi, which is just pi times a0. So what have we learned? We have learned that if my function f was given by this relation, then you have that a0 is equal to 1 over pi, the integral on one period of the function f. Okay, you've got all the details of what we've just done. We integrate, that's what we obtain, and each of these integrals are going to be 0 by parity and periodicity. Okay, so we've got, if that's function f is represented by a trigonometric series, the constant term would be given by this formula. So now let's use a very similar technique in order to find the other coefficients of my trigonometric series. So we're going to integrate the whole expressions on both sides, but multiplied by cosine of kx for some k. Okay, so that's integral between negative pi and pi of f of x times cosine of kx dx. Okay, so same stuff on the other side. And so I multiply that whole stuff by cosine of kx, right? So that's just going to be, sorry about this, so cosine of kx dx. All right, so what do we have then? So then it's going to be, so we get minus integral between negative pi and pi of the constant term times cosine of kx dx plus, well, you know how we proceed in order to be able to write complete linearity using one of the theorems that we saw earlier. So that's going to be an integral of cosine kx cosine nx dx negative pi plus the integral, well, plus the bn, maybe we could write it this way, plus bn times the integral negative pi of, so the sinus of nx times the cosine of kx dx. Okay, so let's compute these integrals. First of all, maybe an easy one to see is about this first one. It's again going to be, well, a0 over 2 times a primitive of that cosine, so 1 over k sinus of kx. And that's still going to give you a 0 because the sinus anyway is equal to 0 at both ends. Okay, then which one can we do? We can treat that last one, right? Here I've got a sinus times a cosine. So how could we do that? To compute this integral, you can, for instance, remark that the cosine is an even function and the sine is an odd function. So the result of this product is going to be an odd function, so that when you perform the integration, you're going to get 0. But that's also one of the small integrals that I had given you to compute in one of the first worksheets of chapter 2. Okay, and similarly, we had something about this. For this, you can perform a double IBP. And so in order to get back to, well, the original integral, and what you find is that if k is different from n, then this is equal to 0. But if k is equal to n, well, you just have the integral of the cosine square of kx. And so you know that you can linearize this part as cosine 2 times kx plus 1 over 2. So that in the end, what you get is that this integral is equal to pi. Okay, we have a notation that you should get used to by now, something that is like this equal to 1 time, well, we've got pi in the end times, let's use this symbol and I'm going to explain what that is. Okay, delta nk. So this is called the Kronecker symbol from scientist called Kronecker, and this is going to be equal to 1 if n is equal to k and 0 otherwise, which is exactly what we were looking for. Okay, so to sum up, what do we have? We have that the integral of f times cosine kx dx between negative pi and pi is going to be, well, 0 for the first term. For the sum with the cosines, it's going to check only the term, the only non-zero term is going to happen when n is equal to k. So I'm going to have ak times Well, we said that was equal to pi. So ak times pi, and then all the terms with the sinus are going to give you 0. So that we have that in the end we find that ak will be given by 1 over pi times the integral from negative pi to pi of f of x cosine kx. Okay, that's maybe the simplest you could expect. And if you do exactly the same, if you perform the same kind of calculations, multiplying your original formula, okay, instead of multiplying by a cosine, you multiply by a sinus of k times kx, okay, instead of a cosine, you multiply by a sine. What will you get? You will get that all the, and do the integration, you will get that all these terms with a sinus instead of cosine are going to be equal to 0. And all these terms where you have a sinus of nx times a sinus of kx, they are again going to be equal, well, to, you get the same thing, pi times delta of nk, meaning that it's going to be non-zero, well, equal to 1, only if n is equal to k. So that finally that's going to select only the term that has a bk. The bk is given by 1 over pi integral from negative pi to pi f of x sinus of kx dx. So that you know if, so let's go back to the original formula. Okay, that's it. So you've got all the explanations of these. So times the cosine kx, you get the Kronecker function. You get this, so you get the values for ak and bk, right? They are given. These are the formulas we have found, and so that, let's go back to the original formula. So that one. All right. So here you are able, if that equality stands, you are able to find all the a n and all the b n coefficients.